Dr. Zhen,
Yes, absolutely.
If you would like to begin your talk. Let me just quickly introduce you to the audience. Dr. Zhen is a recent graduate from the group of Professor Barthelot. His talk is going to be about his PhD work on bio-inspired architectured materials. I will let him take the stage. Thank you.
Yeah, thank you, Ramsha. Can you hear me and see my slides right now?
Yes, we can.
Okay, great. And thanks for Dr. Moan's last presentation, because he really lays the foundation for my presentation, as I was talking more about how to make those bio-inspired materials. And so today's talk, I will be talking about the design, fabrication, and mechanics of bio-inspired transparent materials, which is mostly my PhD projects. Yeah, so we know that glass is a important engineering materials, but they are also very brittle, and so that's kind of limited them in a variety of applications. And making glass is the weakest component in all those applications. And so we need to improve the impact resistance and damage tolerance of glass and suppress their brittleness. So conventionally, there are two ways to do that. The first way is temper glass. We use thermal tempering or chemical tempering to increase the strength of glass quite a lot. But the problem is glass is still very brittle in tempered glass, and even a slightest damage will cause very catastrophic failures. Another way is laminated glass, where you laminate glass layers with polymer layers. The polymer layers will hold the glass fragments together upon fracture, but the problem is, as you can see in the video, the laminated glass is still behave quite brittly. So we need to find some new ways to overcome the brittleness of glass to make it have an improved damage tolerance. So the concept we are using is architectural materials, and so architectural materials, for example, we have stiff materials, which are stiff and brittle materials such as glass and ceramics, and we also have very soft materials as some elastomers and polymers, and so they don't have a very balanced mechanical performances. So the concept of architectural material is that we combine those mechanically dissimilar materials in one well-defined configurations using some very intricate architecture, so that we can have balance between stiffness, strength, and deformability. So the goal is that we can maximize the area under the curve, which is energy absorption of the materials. But the thing is that there is like a huge design space for this kind of architecture, so we need to start from some templates. So it's very interesting because nature, like as Dr. Moon just said, that we have a lot of interesting architectures and very extraordinary material performances. And many of those hard biological materials, they are made mostly by brittle minerals and very thin, weak protein interfaces. But their mechanical performance is quite great, and they are simultaneously stiff, strong, and very tough. So this actually provides a very good to design such architectural materials, and we can see some examples of those architectures in biological materials. For example, Nacre, they have a brick-and-mortar structures and triggering some toughening mechanisms such as crack bridging and tablet sliding. And we have a Cross-ply structures in fish scales and in many like conch shells, and they have a crack bridging and crack deflection as a toughening mechanism. And we also have this kind of helical twisted structure, which is twisted helical structures, which commonly find in, for example, mantis shrimp, which we call it bulligan structure. And this is also like triggered crack twisting and crack deflection as the toughening mechanisms. So it's very interesting that, but we need to duplicate those structures and also mechanisms in those biological materials. Actually, there are actually decades of efforts to try to duplicate those structures and mechanisms in those biological materials. We have freeze casting, we have self-assembly, we have recently vacuum filtration and sintering. We're using like magnetic and electric field to assist with building architectures. But all those fabrication methods, they usually have a very limited structural control compared to biological materials, and in contrast to the minor content in biological materials, which is very high, usually up to like more than 90%. In those synthetic materials with those fabrication methods, they usually have relatively limited minor contents. So that leads to two problems. The first one is that they usually tend to lead to localized deformation, and usually only crack deflection was triggered in those synthetic materials. And this kind of limited the energy absorption and deformability. The other problem is mostly associated with transparent architectural materials. For sure, we can make very thin film materials which looks transparent, but all kinds of thin film materials can look transparent. But if we make it into a bulk material, then the problem of the limited structure control will causing some problems in transparency. As you can see here, it's very milky, and you can see some kind of defects here. So the overall goal, like one of the goal of my project, is actually to solve these two problems, to have like a delocalized deformation and to duplicate like many more toughening mechanisms in those biological materials and to make it transparent. So the outline is I will talk about fabrication and also some of the architectures I'm exploring, and finally impact resistance Nacre-like classes. For fabrication, we to generate highly controlled architectures, we use laser engraving to carve those micro cracks into the glass sheet, and those micro cracks will form into an area of micro cracks to form like a weak interfaces, and then it will form the structures as we wanted. And then we laminated those engraved glass sheets together, highly controlled way, and then we can form a three-dimensional structures. And as you can see that all those geometry and arrangements of those building blocks with laser engraving are highly controlled. You can highly control the relative alignments, and also you can control exactly the geometry of those each building blocks. And also the three-dimensional alignment of the building blocks when doing the lamination is also highly controlled by some assisting fabrication tools. So the second part of the fabrication is to choose the right material, especially for the interface material, because in those biological materials, those organic soft interface is really important. For example, in Nacre, they are actually weak in strength, but they are highly deformable in shear and cause some using shear deformation to dissipate a lot of energy. And the same criteria also applies for our interface materials in those architectural materials. We need to be transparent, and we have good adhesion. Should have good adhesion to glass, and it should have relatively low stress to shear, and should be highly deformable for sure, like similar to the protein interface in Nacre. We test a variety of polymer adhesive, and some of them are quite brittle, and some of them are too strong for glass, and usually leads to glass fracture. So the best choice we have is thermoplastic elastomer called EVA. They are quite highly deformable in shear and have relatively low strength, and then it has a hardening which can help on the delocalization of the deformation. So this is a general comparison with our method comparing to other synthetic method, like fabrication method. So our method has a highly controlled geometry and highly controlled structure, which is even better than biological materials. And our mineral contents can be more than 90%, and which is close to biological materials. but we also achieve very high deformability, which I will explain more in the future slides. So we secured, we have like a very good fabrication method, and so that we want to try some specific structures. The first one we tried is the Cross-ply one, which is commonly found in, for example, Puncture, tooth enamel, and fish scale, as I mentioned. And those Cross-ply one will trigger a lot of interesting mechanisms such as perforation and crack deflection. And here is the bilayer Cross-ply glass we manufactured. And you can see it's very transparent, but actually you can still see some interface if you look closely. But overall, it's very transparent comparing to laminate glass. It's almost no difference. So what's more important probably is the mechanical behaviors intention, as you can see here. For laminate glass, is as expected, it behave quite brittly with acoustic failure, although have high strength. For pure EVA, it has very low strength and very deformable. What's interesting is for our Cross-ply glass, you can see the mechanism totally different from laminate glass. It has a kind of like applied rotation and slidings, and which leads to a very high deformability and also very decent stiffness and strength. So overall, like the Cross-ply glass, we are made of more than 93% of glass, but we can lead to up to 90% failure strength. So here, like it is like we want to try to identify different deformation modes and to identify what kind of mechanism is dominant in certain configurations. So we test like we varied both the ply angles and ply width. And we find out that the ply angle is the most important parameters. As you can see, a relatively low angle, low ply angles, it leads to brittle ply fractures, and has a high, when it leads to like higher ply angles, it leads to translational sliding mode, as you can see here. And so the best design is that has a relatively intermediate ply angles where you can see a large degree of ply rotation. It further leads to a high deformability. So all those deformation modes and mechanical behaviors we can predict by the finite element method and using cohesive law. Using cohesive law to cohesive zone models to simulate the interface. And we find out that the unique mechanism to the high deformability is that the ply rotation will lead to the redistribution of interface attractions and further leads to a global hardening, even though the interface itself is softening. So I will, if you are interested, I can talk more on the detailed mechanism in the QA section. So overall, the properties like intention. So as you expected, we have relatively limited like stiffness and strength comparing to laminate glass. I mean, although it is very much higher than EVA, but what's more interesting is that we had a hugely improved deformability and energy absorption. We got up to 400 times amplification in terms of deformability and up to 100 times amplification in terms of energy absorption, which is a huge improvement, but it is all intentions. So we further examine the fracture behaviors of the Cross-ply glass, and as you can see in the laminate glass, we have a fast crack propagation, unstable and fast crack propagation, because there is no toughening mechanism. But in Cross-ply glass, as you can see, we have a very stable crack propagation. The crack propagation is hindered by crack bridging, crack deflection, as well as interface shearing. Sorry. And what's interesting is we both got an improved crack initiation toughness and also a crack propagation toughness, which is quite interesting because usually we only expect we have a higher bulk of fracture, but we also have higher resistance to crack initiation. So similar to the performance intention, it is also heavily influenced by the ply orientation angles. So at high angles, we have shearing. At low angles, the dominant toughening mechanism is crack deflection. So overall, we have, for crack initiation, we have up to 4 times amplification comparing to plain laminate glass, and in terms of vocal fracture, which is resistance to a crack propagation, we got like up to 50 times amplifications. So, so we have like a very deformable and tough cross-ply glass. The problem is in transverse loadings, it is limited the performance, and we have a relatively low stiffness and strength. So we further like we want to do it like we want to make something great like in transverse loadings, and the first thing we tried is on the brick-and-mortar staggered beams and bandings. And with an adequate design tablet size, we can have a very highly deformable structures. But the thing is, it's in 2-dimensional, so in reality, we need to deal with 3-dimensional structures. So we started with some basic 3-dimensional biological designs, such as cross-ply, polygon, and staggered structures, which served as our starting point of designs. So the first category of designs we tried is continuous ply designs, where for each building block is a continuous ply across the whole samples. So this continuous ply design actually shows, unfortunately, shows limited deformability and limited strength, because all the damage was local due to the fracture of those glass plies. All the damage was localized in near the puncture side, and all the other volume was not involved in taking the load. So we need some improvements. So we know that all the the brittle glass ply fracture is caused by the flexural stresses in those glass plies. So a very straightforward way to think is to reduce the flexural stress, and then it's by segmentations we actually cut those continuous plies into segmented building blocks. In this way, that we actually substantially improve the toughness as well as the deformability of the cross-ply glass, cross-ply, continuous ply designs. And which is more interesting is because usually people think if you introduce more interface into a materials, in architecture materials, you will actually reduce the strength. But in fact, we find out that with there's actually an optimal point where you can improve the strength as well. I will detail it in the later slides. So as we can see that when you just like initially we have improved deformability with the center segment designs, we further improve the size of the building block size. We will have improved strength without losing deformability. But if we further increase the size of the building blocks, then it will have limited deformability as well as limited strength. So the same also goes for the Nacre-like, which is also a kind of segmented designs. So here the picture is more straightforward. As you can see, when the size is too large of the building block size is too large, it has a brittle fracture similar to the continuous ply designs. When we have a smaller like the building block size, we will have kind of like ductile behavior, which is triggered by the interface shearing. So the optimal design will add the transition line here. But the thing is, the segmented design still have limited stiffness and strength. So we want to improve the stiffness and strength as well. And so is it possible like to improving both simultaneously stiffness, strength, and toughness? So we know that all those architectures, they only works when they are loaded in tension. When they are loaded in compression, all those interface shearing, those fascinating mechanism will not be triggered. So in transverse loadings, the top surface is actually loaded in compression. There is no need to use the architectures. So the most straightforward way is to replace them with plain glass. And because we know that although glass is pretty weak in tension, but they are pretty good in comparative stresses. So in this way, we actually substantially improve the strength as well as the stiffness of the glass panels, as we can see here. Although the top surface, which is made of plank layers, will suffer like brittle fractures, but the overall behavior of the glass panels, as you can see here, is still very deformable and dissipates and absorbs as much energy as the segmented designs, as you can see in the curves here. So the overall, like we're starting from continuous ply designs, and we evolve to segmented designs, and we further evolve this to hybrid designs where we have substantially increased stiffness strength. So overall, we have 500% increased stiffness comparing to our starting point, and we have 70% increased strength compared and 200% increased toughness. So we can actually conclude our design principles where for architecture layers, we need to find the transition line between a brittle ply fracture and interlayer shearing. And for all our designs, we need to place the suitable architectures based on their local stress states so that we are optimized the overall layout of the structures. So we apply these design principles and we want to make some impact resistance glass because usually glass are suffer from their very poor impact resistance. And we start with the Nacre-like designs where we know that Nacre is very good at the seashells are very good at taking the impact loadings and by the large scale tablet sliding. And we designed two types of those Nacre-like tablets. The first one is square one, and the other one is hexagonal one. So we are the first one to make those bulk transparent materials, the Nacre-like transparent materials, and you can see the transparency of the Nacre-like glass, which is actually quite close to plain laminate glass, although a little bit lower. But we can tune the tablet size and the geometry to actually approach the transparency of plain laminate glass. So the overall, like the designs following up the design principles we just we proposed before, and using hybrid designs and segmented designs. And you can see that the overall trend is similar to what I just presented in the previous sections. And we finally got like a stiffness strength close to plain laminate glass. And but our energy absorption and puncture is greatly improved by 2 or 3 folders. So but the thing is, we want to confirm which kind of mechanism is most dominant in those in the Nacre-like glass panels, and we do like a micro CT scannings on the puncture samples, and we can find out that for plain laminate glass, we can see there's very limited, actually very few slidings of the glass fragments, and which is also localized near the cracks. And for Nacre-like one, we can see there is a large scale of tablet slidings and distributed to over the whole volumes of the samples. And we can actually quantify the energy absorption from tablet sliding based on the sliding distance we computed. And we found out that the energy absorption from the tablet sliding is 2.4 times higher than plain laminate glass, which agree with our the result from our puncture test, which confirms that the large scale tablet sliding is the most dominant toughening mechanism in such Nacre-like glass panels. Then we further move to the high strain rate impact test. And comparing to a variety of commercialized products. And so for comparing to plain laminate glass, it's still brittle, but the glass fragments, as you can see here, is holding together. But all the other, including acrylic glass and tempered glass, borosilicate glass, strengthened borosilicate, they all behave very brittly, especially for tempered glass. But our Nacre-like glass, you can see upon puncture, upon impact loadings, it actually it deforms quite similar to what we observe in the quasi-static text. You can see a large volumes of tablet sliding, which is kind of like a plastic zone around the puncture site and dissipate a lot of energy. So our Nacre-like glass can absorb energy in an impact more than around 2 times higher than laminated glass and tempered glass. So yeah, that's basically conclude my presentation, and thanks a lot for the support from my group and Professor Barthelot, and also external helps from industry as well as from other professors and technicians. Yeah. Thank you.
Thank you very much, Zhen. We have some time for questions because we're anyway at a break. Can I quickly ask one?
Sure.
I don't work in the area, but so the idea is to create weak interfaces in the glass by etching specific patterns, is it?
Yeah. I mean, it's not exact etching, but it depends. Like sometimes we engrave, like I can show probably some pictures to better illustrate yeah. I think this size is great. Sometimes we etching a trench on the top of the glass layers, and then we mechanically separate them. Sometimes we engrave like it's more like area of micro cracks within glass. Yeah.
So after impact, for example, in your video, there is still permanent damage, but the structure as a whole is intact.
Yeah, it depends on how you define permanent damage. I mean, so as you can see on the last videos, like so here it's not like fully reversible deformation for sure.
Mm-hmm.
There's some past deformations.
Right.
Yeah, but it's not like the glass, which is it's completely fractured. So it's kind of like that. It's more like elastic and plastic deformations. Yeah, okay. Some degree of elastic deformation, a little bit plastic deformations as well.
Dr. Nagamani has a question. You can speak up.
Yeah, thank you for a very nice presentation. I had a question about how you measure work of fracture. Is it the area under the load displacement curve, or is there anything else that you?
The work of fracture. Yeah. So the work fracture is the area in the curve, but the thing is in the fracture test, because the EVA, like the interface material we are using, is high deformable. So you can almost never fully fracture the whole sample. So you will see the load will keep on going forever. So, but the thing is, at this point, all the architectures are actually damaged already. So we just assume that yes, no need to continue. So when all the architecture was damaged and there's no recovery, then we assume that the architecture failed. Then we compute the energy before that point, and using this as a work of fracture divided by the fracture area for sure. Yeah.
Right. So you have a notch specimen, right? So you maintain a constant notch length so that you.
Yeah. We have a notch length. The notch is like around 2 millimeters. I mean, there's a U-shaped notch, and so the little pre-cracks here is 2 millimeters. I kind of forget. Like I think I have the data on the whole specimen. Yeah, here. This is the design of the specimen.
Right. So how do you make the notch? My last question.
The notch is laser cut.
Okay. Yeah. Thank you so much.
Yeah.
Dr. Vignesh had a question for you.
Thank you. Thanks for the great talk, Zhen. I just have a question about the scales you're dealing with. So if I understand this right, you are working with controlling the structure, you're controlling defects at the structural scale to control toughness, right?
Yeah, I mean, you can consider it as controlling the defects of the structure because
right, so my question
when we engrave when we engrave those micro cracks, the micro crack itself is defects. But if you place the defects in a very controlled and very well designed way, then it actually contributes to your mechanical performances.
So my question on that note is there a complementary effort at the material scale, for example, where you can put in inclusions into the material, that would it complement the structural scale micro cracks that you're putting in, or would that be an impediment?
The inclusion you're referring to is, you mean, what kind of inclusion is that?
I'm talking atomic scale control, where you try something like borosilicate glass versus a different type of atomistic composition. Would that in any way, so I could imagine that would to some level control how cracks propagate inside the system, at least at the very, very small scales. I'm wondering if the scale that you are working with and the atomistic scale can somehow interface to further improve your toughness properties.
Yeah, I think it's possible because the architectured materials like I presented here, the scale of each building block, each like base building blocks is the properties of the building blocks is limited by the material level properties of the for example glass. And if you can enhance the material level property of glass, for sure you can further improve the performance of the overall structures. Yeah, for sure.
Okay, thank you.
Yeah.
Hi, Suresh, please go ahead.
Yeah. Okay, Dr. Yin, very nice talk. My question is the following. Towards the end, you said that local stress state could give you the better performance because you could actually tailor the structure or pattern based on the local stress. Can you shed light on that?
Yeah, for sure. I know, like I probably explained it quite too simple. I mean, the local stress state, for example, I think I can take the hybrid design as an example. Probably it would be better. So if you have like a beam or a panel when you do a punctures, if you don't even need to look at the let's say it's the homogeneous panels or homogeneous beams. Then when you take the bendings or puncture loadings, the top surface will be on compressive stress, and the lower half will be not exactly half, but lower layers will be in the tensile stress. So what I mean is that you can it's more like iterative designs. The first is a homogeneous beam, and you take a load, and you know that what kind of the stress state based on its locations. So we can optimize the local structures based on the stress state from the last iterations. And then we examine the stress again, and then we do the next iterations and to further improve the overall response. I mean,
so you can visualize, you can visualize spatially heterogeneous patterns, right? Eventually, if you optimize. Yeah. Okay, thank you.
Dr. Zhen, I have a couple of questions. On slide number 10 or 11, you showed a couple of pictures where these we had a movie that showed that these interfaces were lighting up, right? So at the end of the test, right, these interfaces are basically the locations where damage accumulates. Is that right?
I think it's not exactly the damage is located, because when you engrave the for example interface here, so initially those two two glass plies are actually it's not joint, but it's very closely packed.
Okay. So
the interface itself is very thin. You can barely see them. But when you pull it, so the plies is actually separated, getting like distant from each other. Then, and also the shear deformation of the interlayer and when it deforms, it will have some plastic deformation. Once it has plastic deformation, it will become a little milky, and that milkiness is what happens. Yeah, I think yeah.
And somewhere you said that there was some way in which you decide what's the size of the building blocks, right? The square or the patterns that you put in.
Yeah, we actually built some analytical models as well as finite element models to give us our directions. And so as you can see, like this is like working is a model I built before to predict on the how to predict the stress distribution on each this kind of overlap, and to predict behavior, to give like design guidelines to like what kind of the relative, for example, aspect ratios and the overlap size of the building blocks. And there are some other some like those kind of design guidelines to. So, but those models like are not that important because it is still like not. It's based on a lot of assumptions. So but they gave us a approximate range of the kind of parameters we should choose. Like but those models are not that important. I mean, comparing to the final products. Yeah.
Okay. Well, thank you very much. I also like that you integrated art into your presentation. I saw your painting and your signature on the last slide. Is that right?
You mean this one?
Number 3, huh? Exactly.
yeah. So yeah, I like drawings. So yeah.
All right. Thanks very much for your talk.
Yeah, thank you. So I should stop sharing?
Yes, you may.
Okay. Yeah, thank you.